Now let's try to use actual data. So please download US car 1978. This is 1978 actual automobile data in US market. When you are trying to calculate a confidence interval, always it's important to know what kind of variable you have in your hand. We are interested in mile per gallon and price of this car, and these variables are continuous variable. And for some regions data using just means, but which means this is continuous means. It's a little bit confusing, so I believe as data will change later the label. But in theta, the means is actually continuous means. So if you have your variable in the form of continuous means, and you can check means, and you can define your variable names. So now you're interested in MPG and price level, and you can check computer interval type as normal, and you can check computer level, and other thing you can just keep default. You can do in this way, or simply you can just type on your command window CI confidence interval, and you are interested. So then you need to assign. So you need to assert. So this variables is continuous means, and you are interested in MPG and price. Then theta will return. So standard error of mean of MPG looks like this. So you can just plug in this number in the formula we already have discussed already. You can find same outcome, but simply you see 95% confidence interval of your MPG is 19.96 and 20.64. You can see here. So this is 95% confidence interval for your mile per gallon. So from your sample, your mean variable is 21 and standard deviation is 0.67. And based on this information, and by adding your option of mean continuous means, you can find confidence interval very easily. If you'd like to obtain wider confidence interval, so which means you allow more degree of ignorance, or degree of your error. So which means if you increase your confidence, then your accuracy is going down. So if you are trying to make your prediction pinpoint, then your confidence is going down. But if you are making very wide, very broad guess about something, then now you don't have to worry about your confidence. So in fact, in this case, just use comma. This means now option and level 99. Then you can see data will return 99% confidence interval, which means what compared to our previous one. Now, this 99% confidence interval is actually wider. So this is a continuous means. Sometimes you can also break out confidence interval according to by group. So if you take a look at original data, then you can see whether this car belongs to group of domestic cars or foreign-made cars. So you can just assign same option, but you can click by and you can assign what's in a group variable. So group variable is now the variable name foreign means whether this car is made in US or other foreign company. So you can just put foreign here. And data will return. This computer interval is for domestic car, and this is computer interval for foreign car. And if you compare that, now domestic car, your MPG is now between 1850 to 21/15. So this is now domestic car. But your foreign car is now 21.8 and 27.70. So you can see that now with 95% confidence interval, now maximum value, so maximum MPG of your domestic car is lower than your minimum value of a confidence interval for foreign car. So which means now two different confidence interval, they don't overlap each other. Which means with 95% confidence, you can see that this domestic car's MPG is absolutely lower than foreign car. So you can see now with the 95% confidence interval, you can see that if you are buying foreign car, then you will have better energy efficiency in terms of now lower MPG. So you can just compare this is so now this range, and these two range are not overlap each other. But price, okay, you can overlap, so there's no big difference. However, in terms of MPG, the maximum confidence interval of domestic car is actually lower than minimum confidence interval of foreign made car. So that's kind of your conclusion. If you are doing on command window directly, then first you define, hey, so now please using foreign variable as default group variable. Then please sort. And after that, now you have a colon, and then now comes the interval means MPG price, and also I try to see also total. Then now you can see entire result on one single table. So this is the case for when your variables are continuous variable. So this is usually now we call the integer. Okay. Sometimes your variable may be just proportion. So it's percentage. And proportion is in fact mean or average of some kind of likelihood. For example, now if you are interested in baseball, then baseball, the best information to measure their performance is batting average. And batting average means now how many chances they were given and how many times they convert their chance into safety hit. So, for example, now the first batter, James Vasquez, now he had 206 at bat, and now he was successful 70 times. So his batting average is what? 0.340, which means the likelihood of his success is 34%. So proportion is kind of mean, but which is very useful for your estimation about some likelihood of chance, given the fact the history will repeat. So proportion is what? Between 1 and 0. And 1 and 0, which means what? This is equal to probability. So if you're interested in probability, then now you're interested in proportion. And if your variable is proportion, and now you are trying to study confidence interval for proportion, then you should use binomial distribution rather than normal distribution. Normal distribution is continuous distribution, so it looks like this. But binomial is either 1 and 0, so it looks like this. So let's take a look at your promotion.dta data. So this is data on the company's employees, including variable making whether employees was promoted last year. So now, how many employees were actually promoted? And based on this information, we are trying to infer what is the likelihood of new promotion in this year. Usually, this kind of data, you can see either 0 or 1 variable. 0 is failure or something not happen. And 1 is success or something happen. And you can see that now if you take a look at approval rating for political candidate, then you can see its percentage. And such approval rating is coming from where? Whether this individual will vote for Republican, or maybe you can do also Democrat, okay, reversely, or otherwise. So 1 and 0, this kind of variable we call dummy variable. So in fact, do, not do, exist, not existing, yes or no, that is not number, but now we are trying to assign some numerical variable, so 1 and 0, and by adding 1 and 0, then if we just summing up, then sum of these 1 and 0s will be converted to what? Proportion. It's like approval rating. Then your approval rating for specific candidate is what? Measured for chance of being elected. So now whether who will be winner in this election, then now that chance, okay, we can make inference from approval rating. And if you take a look at promotion data, then you can see, okay, if this employees was promoted, then it is coded as 1. If not, it's coded as 0. So this is a kind of binary variable, or sometimes we call it a dummy variable. And because if this variable is the binary variable or dummy variable, then we should use binomial distribution to test this kind of statistical phenomenon. So you can see that if your variable is continuous distribution, then now you are using normal. However, if your variable is a discrete distribution like the binary, then now you should assign binomial interruption. Why? Because binomial, then now you can ensure your confidence interval will bounded between 0 and 1. So once you load your data, then you can see this window. Just check proportions here. And now your variable, so which means what? Your binary dummy variable, whether promoted, so promotion variable, and 0 is not non-promotion. If you calculate by your hand, then your proportion is about 0.012. So it's pretty low. However, we are not sure whether this previous history from sample perfectly reflect entire likelihood of promotion. That's why we are using statistical analysis. So compute interval, then now you can just keep as default, okay? So you can just exact and 95 first compute interval. Then now you can see that 95 compute interval is what? In fact, your minimum, your inference is about 1%, but your maximum is about 32%. So which means between about 1% to 32%. Which means if you are doing same test 95 times, still the chance of being promoted is less than 32%. Less than 32%. So which means it's not 0, but definitely now this is hard. And later you can compare this confidence interval with some kind of claim from HR. Then now whether HR is not telling a truth or not, you can easily verify. So here you will need 20 observation, and within this observation, now your proportion is just only 0.1. And this is standard error, and then now this is what? Now your chance is not between about the 0.012 to 0.31. So which means now, according to your data, you see about 10% of promotion rate. So based on your sample rate of a 10% promotion, then now you can make a statistical inference that actual promotion rate should be between 1% to 32% with a 95% confidence. And simply you can do that. So comes an interval, but now you are defining, instead of means, okay, you are defining proportion, and this is a variable name promoted and exact. So that's good. Now, remember when we use US car 1978.dta, that time we remember the foreign variable is whether it's domestic or foreign manufactured car. So in this case, you can also simply CI proportions foreign and the price, and if you enter the price, then you can also compare, okay, which car is more expensive, okay, foreign car or domestic car, and exact. So you can do, okay, same analysis. Now, we have Petri data. So Petri data is the data on number of bacterial colonies on Petri dish. Now this is important. This kind of variable is not continuous variable. This is actually count variable. Count means we have 0 times, 1 time, 2 times, 3 times, 4 times. We don't have minus 3 times. We don't have 2.37852 times. We have only what? Non-negative integer. So if your variable is count variable, then, so for the count means what? If your variable is now 0 times, 1 time, 2 times, 3 times, 4 times, then you are using statistical distribution called Poisson distribution. So Poisson distribution looks like 0, 1, 2, 3. So Poisson distribution should be used for only count variable. Then we should specify Poisson interval option to Stata. So using the patry.dta, so Stata report, okay, so now you can just open this data set. Then Stata will report now average number of colonies per square is 2.33. And so then now you can just put mean, because it's not proportion, it's actually the mean. But now you'd like to make this Poisson. Then Stata report average number of colonies per square is at 2.33, so it's mean. However, your confidence interval is what? Minimum is 0.16 and maximum is 2.88. So you can see that now with the 95% your confidence, now definitely now number of now bacterial colonies should be lower than 3. However, definitely okay higher than 1 times. So you can see either you expect okay 1 times or 2 times, but not 3 times, not 0 times, with 95%. So if you are playing this kind of test, okay, 100 times, then usually 95% of your trial, you will see either 1 time or 2 times of your bacterial colonies on your Petri dish. So, and then you can see, looks like this. And same thing now, your confidence interval and your interested means is just average, not proportion. But now this is count variable. So now Petri data, you can see count variable name. And then now you need to just assign Poisson option here. Sometimes you just need calculator. So you already know every number. So now this is what your scenario. So now you are reading to soon to be published paper by your colleague. And now your colleague asks you to review his draft. And his table showing number of observation, mean and standard deviation of 1980 median family income for North, East, and West. And now you believe that, hey, maybe you can include confidence interval, then now you can improve your draft. And you already have a number, so now you have 166 cities, okay, in terms of sample, and your average is not $19,500, but standard deviation is about 4,379. Then you can open just calculator, and you can assign this a normal mean, and sample size, sample mean, and sample standard deviation you can add. Then you can find your result, and of course confidence interval, but now you are adding I because now you are using just calculator. You are into the mean, but it's a continuous variable. And now this is what? Number of observation. And this is your mean. And this is your standard deviation. So you can do it this way. What about proportion calculator? So let's assume I'm playing kind of gamble. So we are flipping the coin. So okay, if you had, you are win. If you have tail, you are losing. And I flip the coin 10 times, but it comes up had only once. And now you are shocked. Maybe, hey, maybe the gambler is cheating you. So you suspect. So you try to test whether this gambler is cheating or not. So you are shocked and decide to obtain 99% confidence interval for this coin. And this is time, but now you're interested in whether this coin is fair. If this coin is fair, then your expectation is what? 50% of chance you should have chance of winning. So 50%. Then now we know you should use proportion. It's either head or tail. 1 and 0. Success, failure. Win or lose. So it's binomial. So you can just define proportion and sample size. And now you try 10 times, but now you found one success. And you can see that with the 99% confidence interval, this is now almost 0, but your maximum is what? Over 50%. Which means you suspect, but with 99%, still this is higher than criterion for your fairness. So that's why you cannot blame your gambler while you are cheating, because now with 99%, we are not sure, we are not confident enough to blame this gambler in terms of their cheating. Because now, if this is lower than 50%, then now with 99% confidence, we can say, wow, you are cheating. So this coin is unfair. But problem is, your confidence interval is actually now providing higher chance compared to our fairness criterion of 50%. So it's not 54%, but this is definitely greater than 50%. So then now, with the 99% confidence interval, we cannot say he's guilty. Now, let's assume number reported traffic accident in Riverside over 24-hour period is 27. So let's assume now you are interested in whether we should invest more money for traffic light or traffic law enforcement. And now you are interested now then, how many times, you can expect your traffic accident in Riverside for 1 day. And now traffic accident is number count. So you can use Poisson distribution. Then now you can just put Poisson mean. It's not normal mean, Poisson mean. I think now this is now very similar to your version, but sometimes Stata may change the label. So make sure you are choosing the correct one. And you don't need to worry about sample exposure, just keep one. And now sample event, we have the 27 event, and confidence interval is 95. Then you can see now if we repeat this kind of test 100 times, then out of 100 times, 95% of a chance you will see between about 18 times to 39 times in terms of traffic accident. So let's assume if government is providing budget, hey, so if traffic accident is now on average higher than 40 times per hour per day, then now we will increase budget. But problem is what? Now this one is lower than 40%, so now you are not eligible for applying for increase your budget. And you can see that confidence interval, CII, so it's calculator, means 1. Okay, because like the sample exposure 1, you can just put 1 because this, you can just, because you observe this kind of test just one time, just 1, and mean, okay, 27, and Poisson. So it's exercise. So far, we have discussed about confidence interval. But now, we'll also talk about hypothesis testing. Hypothesis means this is testable statement. So now we are trying to test whether this statement is statistically correct or not. So, which means I would like to prove this statement is correct. However, prove something correct is really hard. Then, maybe it's really easy, it's way easier to disprove. So, in fact, by making successful disproof, you can prove something alternative. So this is called hypothesis testing. So again, always, whenever you are trying to test, whenever you are trying to prove your claim, then first you need to convert your idea in terms of testable statement. And because proving this statement is correct is hard, however, by disproving some kind of alternative statement which is complete with this your hypothesis, then now you can prove your statement. So this is now hypothesis testing. So general logic is what? For example, you believe that now you see some difference between X and Y. You'd like to prove. I'd like to prove X is different from Y. For example, now Y is, for example, let's say it's a male's income, and this is your female's income. So let's assume you'd like to prove existence of income inequality. And income inequality means what? Mean value of man's income is different from mean value of female's income. If you prove this is correct, then now you prove existence of income inequality. However, proving difference is hard, then maybe let's assume, what about disprove equality between, equality between X and Y. If you can disprove this equality, then logically it's same as prove inequality. And this equality we call is null hypothesis. Null hypothesis actually you'd like to destroy. You'd like to disprove. So which means to prove your story. And your story is emphasizing difference. So trying to prove your story of income inequality across gender. Then you are trying to disprove some null hypothesis in terms of equality between two different income groups. So this is a general logic of hypothesis testing. So it looks a little bit complicated, but if you take a look at actual example, then it's very intuitive. And usually this result is called statistically significant at the 5% significance level. So which means what? Income difference. Income inequality between gender is statistically significant at the 5% confidence level. This is general logic of hypothesis testing.